a pretty straightforward proof here, but it can sometimes seem a bit tricky. The question asks us that given that A and B are independent events, show that A complement and B are also independent. So before we get into this proof, let's talk a little bit about independence and how that differs from mutual exclusivity. So let's just quickly draw up two Venn diagrams. All right. Here's Venn diagram one. We have A, B, and our sample space S. And then let's draw Venn diagram two. Similarly again with A, B, and sample space S. All right. So, very often when students are asked, pick which of these represent independent events, because of how the language in statistics works, they generally pick this. This Venn diagram, however, represents events which are mutually exclusive. Now, what does that mean and how does that differ from independence? Mutual exclusivity of events simply means that these are two events which cannot occur simultaneously. Think of this as a coin flip. A coin flips on either heads or tails. There is no intersection in a coin flip. There is no eventuality in which a coin ever shows both a head or and a tail at the same time, right? Another example is rolling of a die. A die will never show a 1 and a 6 on the same roll, right? A die can only show one number at a time. So these are mutually exclusive, a head and a tail, as well as the probability of a 1 and a 6. Looking at independent events now, independent events simply mean that the occurrence of one event does not matter in the probability of the occurrence of the second event. What does that mean? Let's give an example of both an independent and a dependent event. Let's start with the same coin flip. Let's think of flipping two coins in a row, right? And let's look at the probability that we get a heads on those both. So on coin A, the probability of getting a head is zero point 0.5. On coin B, the probability is zero point 0.5, which means the probability of getting two heads in a row is the product of those, which is going to be our intersection, which is going to be 0.25. Now let's look at a dependent event with every statistician's favorite tool, the bag of marbles. So let's say we have a bag with four marbles. Two of the marbles are striped. The probability that we pick a striped marble from this bag will be 0.5. If we put that marble back in the bag, stick our hand back in, the probability that we'll pull out a unstriped marble is again zero point 0.5. However, if when I picked that striped marble at first, let's say whatever marble we picked first, we remove it from the bag, right? And then pick again. So we go in and our probability of picking a striped marble is zero point 0.5 and we remove that marble from the bag. Suddenly, the probability of us picking an unstriped marble goes up from zero point 0.5 to 2/3. And if I had picked a striped and unstriped marble first, then my probability would have fallen to 1/3, which means that the outcome of the second dip into the bag is dependent on what marble I picked on the first dip. So now that we have the difference between independence and mutual exclusivity down, let's formulate this proof. So, as we said, with the flipping of the two coins, if an event is if an event is independent, we can represent it in the following way. The probability of A multiplied by the probability of B, if two events are independent, is equal to the probability of A intersect B. So this will form the crux of our proof, right? And that being said, what we're trying to prove is that the probability of A complement times the probability of B is equal to the probability of A complement intersect B. Hopefully, I did not write that too far to the left, but in case I did, to the right. In case I did, let me pull it back over. So that's what we're trying to prove, right? So the very first step, we can see that we have, let's call it a loose A complement here. So we need an A complement over here. So let's decompose this probability of A here, and let's call it 1 minus the probability of A complement. As we know, A complement is just equal to 1 minus A, or the probability of A, right? Moving this across, we'll get, let me just write in this, right? Moving this across, we can inversely see that 1 minus the probability of A complement also does give us the probability of A. Perfect. All multiplied by the probability of B is equal to the probability of A intersect B. Multiplying the probability of B through this, we get the probability of B minus the probability of A complement times the probability of B is equal to the probability of A intersect B. You can see we're starting to look like over here a little bit, right? So if we add this term to both sides and subtract this term from both sides, what we end up with is the probability of B minus the probability of A intersect B is equal to the probability of A complement times the probability of B. Now, we're going to decompose this probability of B here. I'll show you what we're going to decompose it into first, and then we can look at it intuitively. So this decomposes into the probability of A intersect B plus the probability of A complement intersect B. And you can kind of see where we're going with it from here on out, right? But let's look at this intuitively by drawing yet another Venn diagram. So looking at this Venn diagram, this one is hideous, I know. Let this be A and let this be B. Now, let's look at this first one here. A intersect B. A intersect B is this area here in the middle that I've made unnecessarily tiny, right? Now, all we need to get the entirety of B is to fill in this region here. This probability is a probability of A complement intersect B. Well, what is A complement? A complement is everything out here, including B, which is not a part of A, right? However, we did say A complement intersect B. So the intersection of A complement and B. The only place that is outside of A but inside of B is this leftover region here, which, when added to the intersection of A and B, forms the entirety of the probability of B, or it forms the entire circle of B. So, remembering this proof, we can simply rewrite this with the minus probability of the intersection of A and B is equal to the probability of A complement times the probability of B. And of course, this here cancels with this here, as this is negative, which leaves us with the probability of A complement intersected with B being equal to the probability of A complement multiplied by the probability of B, which then proves that A complement and B are independent events for all A and B are independent.